Hello everybody. This video is just going to go over the Unit 2 study sheet, which covers chapters 14, 15, 16, 17, and 18. First, we can start with the terms to understand section. This is just made up of all of the boldface terms that we encountered in our lecture notes, plus a few extras that I wanted to call attention to. First off, with stellar parallax, this is a concept that we can link back to Unit 1. It is the idea that if Earth is actually moving around the sun, for stars that are relatively nearby, we should be able to measure a parallax angle that shows the slightly different line in sight that we get in January versus what we would get in July. The parallax angle is what we can measure directly by just watching a star's shift over the course of 1 year. And we know that we can use that to calculate the distance to a star in parsecs. The parsec is the distance unit that communicates how far away a star whose parallax shift is exactly 1 arcsecond is when measured from Earth. Next up is magnitude, which is broadly just a synonym for brightness. It also refers to the magnitude scale that we can use to compare stars to one another based on their brightness. The more negative a magnitude, the brighter the star is. But any one star has 2 magnitudes, absolute and apparent. Absolute is the one that corresponds to luminosity. It's also something we can define as the apparent magnitude a star would have if it were exactly 10 parsecs away from us. Apparent magnitude describes how the star looks to us from Earth, so it can't give us a description of how energetic that star is. Next up is apparent brightness, which communicates the same information as apparent magnitude, but brightness is something that we can correlate to luminosity, the next term, where luminosity describes how powerful a star or an object is. Brightness describes just how radiant it looks to us when viewed from a certain position. Luminosity is also one of the quantities that we can put on the vertical axis of an HR diagram or a Hertzsprung-Russell diagram. That is the graph that we can use to get a visual representation of not only how stars compare to each other, but a sense for where that star is in its lifespan. Spectral type is one of the quantities that we can list on the horizontal axis, where the spectral types from hottest to coldest are O, B, A, F, G, K, and M. Luminosity class is the one that we could correlate to a Roman numeral so that we could communicate where a star is in its lifespan. Roman numeral 1 was for supergiants, 2 was for bright giants, 3 is for giants, 4 is for subgiants, and then Roman numeral 5 is for the main sequence. That is the section of the HR diagram that cuts from more or less the upper left-hand corner to the bottom right-hand corner. And the one thing that all stars have in common that show up on that main sequence is that they're still relying on hydrogen fusion into helium to produce the bulk of their energy. As that starts to shift, as a star gets closer and closer to the end of its life, then hydrogen fusion doesn't actually stop. It's just not the only type of fusion that's going on anymore. Multiple and binary stars, this is just a term that we can use for stars that are grouped together in groups of either 2 or more. Binaries can be categorized as either visual, eclipsing, or spectroscopic, where there's not really an inherent difference between these binaries. The term just refers back to how they were discovered. So a visual binary is the case where we can actually see 2 stars orbiting some shared center of mass. The eclipsing binary requires different geometry because one star has to pass right in front of the other one so that we go from seeing light from both stars to seeing light from maybe just one star at a time, and then periodically it loops back on itself. And the spectroscopic binary is the type that just reveals itself when you look at the absorption spectrum for this 2-star or multiple star system. What appears to be just one absorption line is revealed to be overlapping absorption lines coming from 2 separate sources. Depending on how long it takes for those spectroscopic lines to go from overlapping to being as far apart as they can get, and then back to overlapping. That gives us information about the period for the binary system. We're taking advantage of or really recognizing the Doppler effect when we use spectra to reveal binary and multiple star systems. This is just a term that we encountered for the first time in Unit 1, but it describes how waves change, whether they're being emitted from an object that's moving toward the observer or moving away from the observer. The Doppler shift is the actual numerical difference between where a spectral line actually shows up and where you would expect to see it if you were measuring it in a lab. Next, we have pulsating variable star, which is more or less a catch-all type of category for different subclasses of stars that all have something in common, and that thing in common is pulsation. So that literally means that the radius of the star is increasing and decreasing on a periodic basis, and as a result, the luminosity of that star shifts. Variable stars are not, they don't change on time periods that you would recognize just by chance. You need a light curve to reveal this change in intensity. Cepheid variables are a subcategory of pulsating variables in general. They're important to our discussion specifically because of the relationship between their pulsation periods and their luminosities. That means that once we recognize that we're observing a cepheid, we can measure its period and then determine its luminosity before we ever know how far away that star is. That's what makes cepheids so useful as standard candles, which is just another term for items whose luminosities are known independently of their distances. And pulsating variables, including cepheids, are found in a section of the HR diagram called the instability strip. Next, we have the two types of clusters, open and globular, where the open cluster is the type that has a comparatively small number of stars that tend to be larger in mass, which means hotter, bluer, more luminous, and then the consequence is that they last for a shorter amount of time compared to the globular cluster. We're going to say more about these in Unit 3, but globular clusters are made up of more densely packed stars in higher numbers that tend to be smaller, redder, dimmer, colder. So these are the types of stars that can last a much, much longer time than the open cluster. And the main sequence turnoff point refers to an inflection point in the HR diagram for a specific cluster that allows us to basically pinpoint how many of the stars that were born with this cluster have already aged off of the main sequence and died, and how many of them are still waiting to move off of the main sequence. That gives us some insight into how old the cluster is. Next, we have hydrostatic equilibrium, which is something we first encountered when we were talking about the type of balance that the sun tries to maintain, or really any star, but we framed this by observing our sun as an example. If the amount of energy that a star can generate in its core has to balance the rate at which it can actually radiate that energy from its surface, any change in fusion rate is going to have to result in some change in the radiation rate off of the star's surface. Next, we have fission and fusion. These are the two nuclear processes that can result in the release of energy. But there's one that was far more important to our conversation than the other. That was fusion, because this is the process that's taking place inside the core of the stars that we studied in Unit 2. It's the result of taking two low-mass nuclei, fusing them together, and then the small amount of energy difference between the nucleus you end up with and the sum of the energies of the nuclei you started with. That small energy difference is produced or is released as a photon. Fission releases energy by starting with a high mass nucleus and then dividing it into lower mass nuclei. But there's still a bit of leftover energy that's emitted as light for that process as well. It's just not the process that goes on inside the core of a star. The proton-proton chain is the type of process that we can pinpoint happening in low mass stars, so ones like our sun, that over multiple steps results in 4 hydrogen nuclei turning into one ordinary helium, but with a few byproducts, namely a few gamma ray photons, 2 positrons and 2 neutrinos, which is our next term. The neutrino is the particle that's associated with the proton's loss of charge in the first step of the proton-proton chain. You start with 2 positives, they fuse together, and you end up with 1 positive and then 1 neutral charge. The neutrino is the particle that is spawned when this positive charge loses its charge and goes to neutral. It's got a very small mass, but not one that is literally zero. So as we discussed, the neutrino was a particle whose existence was hypothesized before it was actually detected, because without it, it seemed to unveil a violation of the law of conservation of energy. Next up, we have convection. This is the name of the process that carries thermal energy from the interior of a star closer to its surface. Instead of doing so in more or less straight lines radially outward, convection involves circuits. So you can trace what you can model as loops, where the material that's closer to the sun's core is going to have a higher temperature. So that higher temperature means that the material is going to be more buoyant, so less dense, in other words. It's going to be capable of moving up closer to the surface of the star, but the trade-off is that now that location is further away from the core, so that material is going to go through the opposite process. It's going to become cooler, denser, less buoyant, and it's just going to drop back down to the location where it started. Sunspots are things that we can observe on the photosphere, so the surface of the sun. We can link these to magnetic behaviors, but remember, sunspots look darker not because they are hotter than other surfaces on the sun, but because of the opposite. They are colder, so they emit less light and look dark in comparison to the rest of a star's surface. Next up, we have a solar flare, which is sort of like the solar wind discussed down here, but just, kind of up to 11. You are observing a star as it's releasing not only charged particles, but also gas. And we saw in our notes from chapter 14 that these charged particles and this gas can get wrapped up around magnetic field lines, so that sometimes you'll end up with a solar prominence, which is something that's more of a horseshoe shape. At the bottom of both of the contact points of a prominence, you will always find a sunspot. But for solar flares and then coronal mass ejections, which are even more powerful solar flares, the material that's being emanated from the surface of a star is going to be capable of actually making it quite far away from that star's surface. The corona is the outer layer of the sun. So this is the layer that is outside of the chromosphere, which is the lowest layer of the sun's atmosphere. The solar wind is the name that we can give to the particles that are always being emanated from the surface of a star. Next, we're segueing to chapter 16 here, so we're talking about star birth. We run into interstellar medium, interstellar dust, interstellar reddening. With that first one, the interstellar medium is just the name that's given to the material that separates individual stars in not only our galaxy, but our universe as a whole. So it's not exactly correct to think about space as being completely empty. It has low density gas in it, but that means that its temperature is going to hover above absolute zero. This is the material that eventually will give rise to later generations of stars. Interstellar dust is a part of the interstellar medium, so this is not gas per se, but you can think about this as the spent material that was once a part of an earlier generation of stars that has since died and returned some of its material back to the interstellar medium. And interstellar reddening is the clue that we can look to determine whether a dark spot in space is legitimately empty, which is less likely, or if it's just filled with dust that's doing an excellent job of blocking light from material that's back behind it. If we can look at the edges of a dust cloud and it looks red, that's just evidence of the fact that dust doesn't scatter red and blue light equally. We know that shifting to a longer wavelength allows us to see through that dust, and we're likely going to find out that this isn't an empty spot in space. Instead, it's just a spot that's being blocked. Molecular cloud is our next term here. We can think of this as the starting point for our star formation process. We know that a molecular cloud that is too hot is unlikely to collapse, and one whose density is too low. So the perfect combination is low temperature, high density. What needs to be overcome in order for that initial collapse to begin is thermal pressure. So this is why having a temperature that's too high makes it less likely that a molecular cloud is going to produce a star. Thermal pressure is just one of three types of pressure that were important to our conversation going forward. Degeneracy pressure is the type that we can associate with just trying to pack a lot of material into a space that gets progressively smaller. Radiation pressure is the type that's encountered when photons have to actually move through material and they experience some resistance, and as a result, they build up outward pressure. Thermal pressure is the only one that changes when temperature changes. So it's very important to this early step in the star formation process. The protostar is the center of this collapsed gas cloud that has flattened down in one direction and is eventually going to become the main sequence star, provided this star actually makes it through all four steps of the star formation process. The protostellar cloud is just a term that we can use for that in-between period where a protostar is working its way toward being capable of actually fusing and showing up somewhere on the main sequence. But as we saw in chapter 16, star birth, there are four distinct steps that a star has to actually make it through to successfully become a real star instead of a brown dwarf, which is something that is similar to the coldest, reddest, dimmest, faintest stars that ended up on our main sequence, but they just did not make it through all four of the processes. The Eddington limit is the upper limit to the mass that a newborn star can have, because we know newborn stars are going to land on a part of the main sequence that correlates to a higher temperature, a bluer color, a larger radius, and then a greater luminosity. So that combination means that it's going to be hard for that star to hold itself together. There is an upper limit to this. We believe it's somewhere between 150 and 200 solar masses. It is not anywhere near as well known as the opposite limit, which just defines the minimum mass that it takes for a collapsed gas cloud to actually turn into a main sequence star instead of a brown dwarf. That lower limit is 8/100ths of a solar mass, excuse me. Degeneracy pressure and radiation pressure we discussed a bit earlier, so I'm going to go on to the first stage that a star reaches once it starts to move off of the main sequence. It's either the giant or the supergiant stage, depending on whether you are starting with a star that is below 8 solar masses for the giant or above it for supergiant. They both occur, they are triggered once hydrogen starts fusing in a shell surrounding the core of a star. So the location of hydrogen fusion is what's shifting. Hydrogen fusion never actually stops until that star literally and officially dies. But depending on the mass of the star, if it's a high mass star, multiple fusing shells can form on the interior of the core. Lower mass stars are going to top out with 2, and as a result, they're not going to be capable of reaching as large a radius once they move off, so they'll become giants as opposed to supergiants. Next, we're going to follow the low mass stellar evolution track a little bit to talk about a planetary nebula, which is what you end up with when basically a low mass star allows pressure to beat gravity for the last time, and the star actually separates. Its core is left behind, it becomes a white dwarf. Hypothetically, if we let that white dwarf cool down long enough, it should be capable of reaching the same temperature as space around it. But black dwarfs are hypothetical. They have not yet been observed because our universe is not old enough for that to have happened. The planetary nebula is what used to be the remainder of the interior of this star and its atmosphere. Now, for very, very low mass stars, they become a planetary nebula and a white dwarf without really spending much time as a giant. But for your ordinary low mass stars, so not the extremely low mass ones, eventually they're going to build and build and build a bunch of helium that it initially cannot do anything with. So it's stockpiled in the center of the core. Eventually, the core is going to compress down, relying on its thermostat effect, which makes its temperature hotter. And eventually, it gets to the point where it's hot enough to fuse that helium. This is a relatively brief section time-wise on the HR diagram, but there's a spike that correlates to helium suddenly being hot enough to fuse into more massive nuclei, but the star is going to find some new normal fusion rate that's going to result in a luminosity that's higher than the star had when it was on the main sequence. But now at this point, it has fusion happening at two different locations, helium in the core, hydrogen in a shell. So we can say shell fusion is taking place here. But the end of the road for a low mass star is approached when that core fills up with carbon, because a low mass star is not going to be capable of compressing its core hot enough or down to make its temperature hot enough for the star to do anything with that carbon. Thermal pulses are sort of similar to the solar thermostat effect in that the star is going to try to compress so that its core temperature goes up, but it's not effectively going to make it to that point. So thermal pulses are sort of like the low mass version of a type 2 supernova, which we'll talk about in a few minutes. But this is the event that separates a low mass star's core from what used to be its interior and its atmosphere. Those two quantities are permanently separate at this point. And the destiny of those items is that your planetary nebula is just going to expand. It's going to become less luminous, but it's going to take up a larger amount of space. It's returning some of its material back to the interstellar medium. Some of it will end up sort of locked in that white dwarf. Now, if we come back to supergiant here in the second column, we can follow the high mass evolution path, where there's no equivalent of the helium flash for a high mass star. High mass stars have no problem reaching a core temperature that's high enough for helium to fuse. So initially, in the early parts of that star's lifespan, it's building a bunch of helium that it's stockpiling in the innermost part of the core, but then helium can start fusing fairly quickly without much fanfare. The CNO cycle is something that assists in the production of helium out of hydrogen, but it uses carbon, nitrogen, and oxygen that a high mass star does have on hand in its core, but a low mass star would not. So this is not something that our sun is going to experience. Once that ordinary helium has sort of been assembled in the background of the CNO cycle, now there is the capacity for helium capture, which is something that we discussed when we were talking about the relative abundances of even-numbered elements compared to odd ones. So this points toward helium capture being a more likely process inside of a stellar core as opposed to individual hydrogen nuclei fusing with progressively more massive nuclei. But this is something that the hydrogen fusion is something that's possible. It's just less common than helium capture. And then we get to the type 2 or massive star supernova. So I mentioned beforehand that this is kind of similar to thermal pulses that are going to destroy a low mass star. They're similar in that the interior and the atmosphere of this high mass star are going to be ejected, so pressure beats gravity at this step, leaving behind a supernova remnant, which is very similar to a planetary nebula, but just contains more massive material because of the type of star that produced it. And instead of a white dwarf being the name for the leftover core, a high mass star is going to leave behind a neutron star. So this is a neutron star because the positives and negatives that were capable of staying separate in the white dwarf are now incapable of staying separate. In other words, the mass of this star is going to successfully compress all of those positives into negatives so that you end up with a neutrino burst, but a ball of neutrons, essentially. Now, just like the white dwarf, there's nothing that's going to restart fusion in this neutron star once the stage has been reached, but we do know that some other options are available to stars that are in a binary, and not just in a binary, but in a binary that experiences mass transfer. So, shifting into our last chapter here, the first term that we run into is the Chandrasekhar or white dwarf limit. This represents the upper limit to the mass that a white dwarf can have before it's forced to evolve into something else. And that something else is the type 1 or white dwarf supernova. So, if a white dwarf is in a binary with a star that's still living, when that star reaches either its giant or supergiant stage, it will expand its radius, which means suddenly the distance between that white dwarf and its companion star is physically shorter than it used to be, which means that it is easier for that white dwarf to strip some mass away. Now, I don't see the term accretion disk here because I think we encountered that for the first time in our previous unit, but the accretion disk is just the name for the like swirling disk of material that one star can slowly strip away from another. And specifically, if we're talking about a white dwarf that's in a binary with another living star, every bit of mass that that white dwarf can strip away from its companion is going to be capable of igniting a nova explosion. So this is just quite literally what happens when this gas reaches the still very, very hot surface of this white dwarf. It will ignite that gas over time. It will dim back to whatever its normal luminosity is, but every time this nova explosion process plays out, a tiny bit more mass gets added to this white dwarf, and it nudges it closer and closer to the Chandrasekhar limit, which is 1.4 solar masses. So once a white dwarf is forced to reach 1.4 solar masses through mass transfer, it experiences a type 1 or a white dwarf supernova, which destroys the white dwarf. It does not survive this process. What would happen if we had a high mass stellar remnant instead of a white dwarf as the receiving party? Well, we would have now a higher upper limit. The TOV limit is the name for the maximum mass that a neutron star can have before it's forced to turn into something else. That is about 3 solar masses as opposed to 1.4. And similar to the nova explosion for low mass stars, if you have a neutron star that's in a binary with another star that's still living, when that star becomes a giant or a supergiant, it is also capable of acting like a source for mass transfer, so that this neutron star can collect mass from its companion. Instead of experiencing a nova explosion, the high mass version of this is called an X-ray burst. We're dealing with higher temperatures, more mass, essentially more everything. So the X-ray burst is just like a higher energy version of the nova explosion, but it is also repeatable. But every single time, a tiny bit more mass is going to be added to the neutron star. And once it reaches 3 solar masses, it's going to now become a black hole. So it will curve space-time to the point that we lose the ability to see the object that's producing the curvature. Think back to the rubber sheet analogy that we talked about in class. Now, one thing that I almost skipped over here is the pulsar. This is a neutron star, but one whose rotation and magnetic axes are aligned so that sometimes the magnetic jet points toward Earth, other times it doesn't. So to us, that looks like a star that's blinking from dim to bright, dim to bright. This tends to happen, over periods of up to a few seconds, but as few as a few milliseconds for the very youngest pulsars. But it's worth reminding you that not every neutron star is going to look like a pulsar to us. There is a little bit of luck or serendipity that's involved here. We need the jet to actually point toward Earth sometimes, but not all times. Now, for Stars that have high enough masses, their neutron star stage is immediately going to leave behind something that's too massive to exist as a neutron star. So if that core is already above 3 solar masses, then that item can turn to a black hole without having to take the slow path, which involves a lot of mass transfer. Instead, that happens more or less instantaneously, and we can start to think about why the black hole is possible or why it should be possible by relating it back to escape velocity. We talked about this as it relates to Earth in Unit 1. We found that it's around 11.5 kilometers per second for Earth, but that is the speed that we would have to achieve in order to get something to leave Earth's surface and not end up in an orbit, but instead take on its own trajectory. If we replaced Earth with our neutron star that was 3 solar masses, and we replaced our rocket or whatever item we're trying to send into space with light, then there should come a point where even light doesn't travel quickly enough to make it away from the surface of this dying star. The singularity is the location inside of the event horizon. Think of the event horizon as a separation between the inside of a black hole and the outside. Once you pass beyond that event horizon, all of the matter that makes up the doomed item is going to end up being compressed into an infinitely small location called the singularity. So think of something that doesn't have height, width, or depth to it anymore, but it contains all the mass of the object that made it through the event horizon. The Schwarzschild radius describes the radius of the event horizon. So this is something that obeys a relationship that's a little bit different than the one that we saw for white dwarfs and neutron stars. In both of those previous cases, we saw that the higher the mass of the white dwarf or neutron star, the better it was at compacting itself. So its radius was smaller as a result. The opposite is true for black holes. As you add mass to a black hole, the Schwarzschild radius goes up. Now, for an object that is near a black hole but not inside of it, we can still receive light information from it, but that information and light is going to end up being redshifted gravitationally. So sort of similar to the Doppler effect stuff that we talked about for the first time in Unit 1. And then gamma ray bursts here, this is our last topic. These are events that come in 2 different types. You have like your ordinary gamma ray burst, and then the less common type of gamma ray burst. We can correlate the less common type to interactions in from the center of very distant galaxies. The other type we can correlate to specific but unlikely events. So think about the collision between maybe 2 neutron stars, 2 black holes, or 1 black hole, 1 neutron star. The energy that's released is conceptually going to be somewhat similar to the X-ray burst, but it is going to be more energetic. So we would expect this object to be incredibly bright in the gamma ray part of the spectrum, as opposed to the X-ray, which is still incredibly powerful, but an energy that is one group below the gamma ray part of the spectrum. Okay, on to the backside. There weren't very many new equations introduced in Unit 2. One of them for parallax. This just tells us that the distance of an object in parsecs is equal to 1 over its parallax angle. And that parallax angle has to be measured in arc seconds for this to work out. If you need to calculate a parallax angle from a distance, you can just take the lowercase d and the lowercase p and swap them so that the parallax angle is 1 over the distance in parsecs. Next, we've got the inverse square law of light. This showed up in lab number 5, and when we were talking about using magnitude comparisons to determine the distance to an object. The luminosity of an object is something that we can link to its internal processes, so the rate at which it releases energy, but its brightness is something that depends on our position with respect to that object. So as the separation gets larger, any object is going to look less bright to us. And because that separation is squared here, when we are calculating the distance to an object using magnitude comparisons, there's a step where we have to undo that square by taking a square root. The brightness ratio is the quantity that we can determine when we find the difference between one star's apparent magnitude and its absolute magnitude, and we just raise 2.5 to that power. That brightness ratio is also something that we can set equal to this quantity on the right, so distance over 10, quantity squared. I split this up into 4 different steps in lab number 5. This line just puts all of them together so that we can tell the distance to a star initially by just comparing its two magnitudes, or if we're working in the other direction, let's say we know how far a star is, we can observe it so that we know its absolute magnitude. We can work backward to solve for if we can observe it and observe its apparent magnitude, we can work backward and solve for the absolute. Then these two at the bottom are ones that we first encountered in Unit 1, but they were important again here in Unit 2. Newton's version of Kepler's third law that gives you the sum of two masses that are orbiting with some period p and with an average separation a for the semi-major axis. Last time we encountered this is when we were figuring out how we could measure the mass of the sun just by watching objects orbit it. And we were able to get away with it because every item in the solar system, aside from the sun, is significantly less massive. So this sum M1 and M2 was still pretty much the mass of the sun, just with a teeny bit added. If you use this for binaries where there is no requirement that these masses be very different, then you still need to do one additional step to figure out how much mass can be attributed to star 1, how much can be attributed to star 2. And then mass energy is something we first encountered in chapter 4. It allows us to essentially understand the nuclear process that goes on inside the interior of a star's core. Moving on to concepts to understand, the magnitude scale and how to estimate a star's distance based on magnitude difference. These things are both associated with Lab 5, so I'm not going to ask you to go through the calculation on the exam, but just what each step means and how it gets us to a calculation of the distance, or to the distance of a star, what spectral type tells us and what luminosity class tells us. It's easy to confuse these, but spectral type is the one that shows up on the horizontal axis of an HR diagram, so we know it's communicating the same information as temperature, just in different terms. Luminosity is on the vertical, so it's communicating the same information as absolute magnitude does, but just in a different way. The sequence of spectral types in order of decreasing surface temperature, remember OBA, FGKM. Old bald astronomers frequently give killer midterms. Using magnitude comparisons to calculate distance, that's also associated with lab number 5, interpreting eclipsing binary light curves. Review lab 6 for this one. The period luminosity relation for Cepheids. This relationship is why Cepheids can be used so well to calculate distances. And hydrostatic equilibrium has to do with the balance between pressure and gravity for any star, and the balance between the energy it can generate in its core and the rate at which it can actually radiate that energy off of its surface. How to interpret an HR diagram, really labs 6, 7, 8 all cover parts of this. But remember, we have a few ways that we can tell which stars have the same temperature, which stars have the same luminosity, which ones have the same radius. For temperature, if you can connect them with a vertical line, then they share a temperature. If you can connect two stars with a horizontal, they share a luminosity. And if two stars fall on the same isoradial line, so the ones that cut diagonally from top left to bottom right, they have different temperatures and different luminosities, but their radii are going to be the same. The layers of the sun, working your way outward from the core, you run into the radiation zone first, then the convection zone, then the photosphere, which is the surface of the sun as we can see it. The lowest layer of the atmosphere is the chromosphere, and then the corona is the outer layer of the sun's atmosphere. How the solar thermostat works, remember we saw like a diagram that showed how a star can maintain a more or less like constant fusion rate by managing whether the fusion rate goes above average and then acting to pull it back down, or doing the opposite. If the fusion rate drops down, then its core compresses, temperature goes up. That means fusion becomes more likely than it was previously, and the fusion rate goes up. The sunspot cycle is something we discussed at the end of chapter 14. This is the 11-year period of solar activity where every 11 years or so, sunspots or sunspot activity tops out. We are around the peak of one of the sunspot maxima right about now. How the earliest generation of stars differed from contemporary ones. We discussed in the star birth chapter the sort of weirdly important role that carbon monoxide plays in the formation of stars that are forming today. The earliest generation of stars did not have that to rely on, so they should have required much higher masses. They should have resulted in much higher temperature stars, and as a result, that means that that generation of stars would live a life that is shorter than any generation that comes afterward. 4 steps of the star formation process. This is also a chapter 16 type topic. It is the formation of a protostar. Step 1, 2, convective contraction. Next, radiative contraction. And then the 4th step is self-sustaining fusion. So once that happens, your star is officially somewhere on the main sequence. How to evaluate life tracks for stars based on their mass. We used our sun as an example so that we could trace what we would expect our sun to look like in the very, very distant future, and what it took for the sun to land where it is on the main sequence. Generally, for higher mass stars, the life track is going to be more of a horizontal. For lower mass stars, it's going to be closer to vertical. For our sun, it's a little of both, so like a diagonal. How mass impacts a star's evolutionary path. Think of the flowchart that put together all of our concepts from Unit 2. We know that before a star leaves the main sequence, the steps of the evolutionary path are very similar, but moving off of the main sequence, now the process that applies to stars that are above 8 solar masses is distinctly different from the one that applies to stars below. How low mass stars compare with high mass stars. It's always a good idea to think about where a low and high mass star are on the HR diagram, so on the main sequence in particular. Then once you know where they start, you can start to trace what should end up happening to that star. The one thing that they all have in common is that they're going to get larger in radius and colder at their surface, which means that they're all going to sort of move toward the upper right-hand corner of the HR diagram. But again, a high mass star is going to move in a path that's pretty horizontal. Low mass stars are going to be pretty vertical. In between, stars like our sun are going to be more diagonal. Which evolutionary states are only available to low or high mass stars? And which evolutionary states happen to all stars regardless of mass. Again, I encourage you to go over the flowchart because certain things like white dwarfs, planetary nebula, type 1 supernovae just cannot happen to high mass stars. So it's good to know or to remember which one is on which side, left or right. Which elements are capable of forming in stellar cores and which ones are not. So for low mass stars, we know the end of the road is when their cores fill with carbon because they simply can't, they don't have enough mass to compress down to fuse the carbon into anything more massive. For high mass stars, the end of the road is iron because it would cost that star energy to turn the iron into anything else. How does being in a binary affect a star's evolutionary path? If mass transfer is possible, then that means that a white dwarf in a binary could become a type 1 supernova. It means that a neutron star in a binary could become a black hole. And distinguishing between the type 1 and type 2 supernova, just to remind you, type 1 is the type that happens to white dwarfs. So there's not much hydrogen that's left over at this point in the star's life. When the core explodes, it's going to be primarily packed with carbon. So if we see strong carbon, weak hydrogen, that is a hint that we're looking at a type 1 supernova. If we look at the type 2 supernova and we see plentiful hydrogen, this makes sense because this is the very last gasps of a high mass star's lifespan. So it still has hydrogen in plentiful abundance. If we're comparing the type 1 and type 2 supernova to each other, then the light curve, if you watch how they dim, it's going to be smoother for a type 1 supernova because they all form for exactly the same reason. Because a white dwarf in a binary picked up exactly 1.4 solar masses. The type 2 supernova has some more variation in it, so this is something that's going to happen to an 8 solar mass star, but also to an 80 solar mass star. How pulsar periods correlate with age, this is lab 9, so the younger a pulsar, the less time it has had to slow down. So short periods correlate to fast speeds and correlate to younger ages. How the white dwarf and the neutron star radii correlate to mass compared to a black hole. The black hole is the only one that gets physically larger when more mass is added. Both the others, white dwarf and neutron star, are better able to compress themselves with additional mass, so they get smaller in radius. And how black holes affect space-time. Again, I encourage you to think back to that rubber sheet that we saw in our notes. If we imagine that that rubber sheet is a stand-in for space-time, space-time is 4-dimensional and the rubber sheet is only 2-dimensional, but we can still visualize curvature in that rubber sheet. So if you had a rubber sheet with a ping pong ball on it, it's not going to curve all that much. But if you take a bowling ball, then it's possible it could curve so much that you can see the spout that indicates where the bowling ball is, but not the ball itself.